All right. Seem like we have these 20 people have a quorum. So let us start. Good evening, everybody. Again.
Good evening, sir.
All right. So I'm using this link this evening a little bit putting you out of your comfort zone because the challenge I had previous weeks is that I was very much unable to record the session. And I do like to record a session, have them posted so persons can visit the recording or the tape at another time. Anonymous lecturer? Who's that? Anyway, now that we're using this link this evening, I do have recording capabilities. So this is being recorded as of now. So hope you had a good week and ready to rumble. You'd have had again some time to watch and read posted information. And as I mentioned last class, one of the methodologies that we're going to be having persons, just at your own will for the first 15 minutes or so, share with us what you would have learned. And I'm specifically looking at, so I think I told you guys, amplitude modulations today. Is there anything anybody wants to share in regards to what they would have read, learned, watched on amplitude modulation?
Yes, sir.
All right, so Stuart is in the house. We have a large, or should have a large group, so I welcome persons making comment, but if they start to go in sync, then I'm gonna have to probably use the raise hand method. All right, go ahead, Mr. Stewart.
Okay, so basically, when I read up on amplitude modulation, basically what it is that you're using basically two waves. You have your original source wave, and then you have another wave. I believe they said is typically at a cosine or sine wave that would change the amplitude so that it can travel further distances. They normally use a mixer to combine the waves. So you would have the frequency remaining the same, but the amplitude of your source wave reflects the amplitude of the secondary wave that you use to modulate it.
Okay. Thank you, Sir Stuart. Anybody wants to add? Or anybody actually want to clarify, add, or query anything that Mr. Stewart had just mentioned?
Basically cover.
Basically cover that. There's a lot of things for modulation.
Sir,
Yes, one second.
thing, sir.
I see Miss Watson handles up before you. Miss Watson, do you have a mic today?
Yes, sir. I'm using my phone today.
Okay.
All right. Are you hearing me?
I'm hearing you loud and clear.
I was basically reading, and first thing, amplitude modulation, right? In amplitude modulation, the amplitude of the carrier is varied in accordance with the message, while the frequency and the phase are kept constant. While I was reading, I learned that the envelope of the AM signal, it is used to track the modulated carriers, positive peaks and negative peaks. I also learned that there are three properties of a modulated signal, which are the single sideband carrier, and the vestige modulation. Not sure if I pronounced that properly. You still hearing the noise? I'm shaking that noise. I'm here.
I was hearing, well, we're hearing you. It had a little bit breaking in and out, but vestigial sideband, you mentioned that you mentioned some other properties of some other aspect of modulated, of the as a result of the amplitude modulated wave. And you stated that the wave constitute the amplitude modulated wave constitute the carrier wave and the information signal, and the amplitude modulated wave, the amplitude varies, but the phase and the frequency remain unchanged. In a nutshell, that's what I heard. Am I correct in terms of what you were stating?
Yes, sir.
Okay.
Yes, sir. So for the single sideband modulation, only one sideband is sent and it eliminates the other sideband and the carrier.
Okay.
And for the double sideband, it filters out the carrier frequency and sends both sidebands. But for the vestigial one, only one sideband is transmitted, but only a trace of the other sideband is transmitted. That's basically what I wanted to say.
Thank you. Said a lot. Anybody else wants to add to the Stuart-Watson combination so far? And I mean, remember, this is now the opportunity for you to share with us what you have learned from it, to seek clarifications, or to add, or even we have no fear, even dispute what somebody might even, as long as it is in a respectful format. This is the place to do it. We have about another 5 or so minutes. Anybody want to add to what has been said so far? And now remember, we're speaking specifically about amplitude modulated wave, or amplitude modulation.
So is it that amplitude modulated waves can travel a longer distance than
As compared to? As compared to?
Frequency modulated.
Frequency modulated, okay. That might be true.
Yes, sir. I'm just comparing the AM and the FM frequency and the radius, and I know that AM you normally get foreign station, but FM you can't get it basically, so just thinking along the line.
Okay. And there's a good reason for that, which it's gonna come all out in whatever we do for this semester. And it has to do with one of the property of waves. That's called a wavelength of electromagnetic wave. The wavelength, the frequency varies, hence the wavelength vary. And there's a relationship between wavelength and frequency, inverse relationship between wavelength and frequency. So the higher the frequency, the shorter the wavelengths. The shorter the wavelength of a signal, the wavelengths or the frequency with that short wavelength have the tendency to travel through objects instead of going around the object.
Yeah, it's more penetrating, sir.
If you think about when somebody is doing an X-ray on you, the X-ray actually is a photograph of the skeletal system, right? So what happened is that it actually the X-ray, it's not just a loose word. X-ray meaning that you're using X-ray waves that has certain frequency. Pretty much, so you can say a high frequency, very high frequency in the gigahertz band, And what will happen is that this frequency, because of their short wavelength, they will penetrate the skin, all the tissues, and basically give a scan of the skeletal system. So think about the higher the wavelength, the higher the frequency, the shorter the wavelength. The shorter the wavelength tends to penetrate. So FM wave has a higher frequency than AM wave. And that is why FM wave will tend to hit buildings, trees, mountainsides, and they will not travel over the building, around the mountainside, over the trees as AM wave does, because AM waves are actually have a shorter wavelength, so they'll tend to they have a lot longer wavelength because the frequencies are shorter. But we'll get into that a little bit more. And yes, Anika, that's one thing that we're going to be coming to as well. Which is that AM is susceptible to noise. Yes, go ahead.
Sir, and you left out the fact that that's why 5G is so dangerous, because it has very short wavelength, sir.
There's a lot more to that, and that's a part of a research that I've been a part of, and I'll tell you a lot more about that. It's not pertaining to the class, but it's not as it relates to this class, but it is for knowledge. Sometimes people speak from uninformed position, or sometimes they have a little bit of information, and sometimes no information is better than a little information, because a little information sometimes, you have you ever heard they talk about a Chinese message?
Yes, sir.
It gets a lot of twist and turn to it. And what was said initially and what was eventually heard, totally different kettle of fish. All right, anybody else want to add to the convo in regards to what I've learned about amplitude modulated wave? How about why is it that we need it?
For example, when we spoke about the distance, for example, that it has to travel, as the waves travel across a certain medium, they can have a lot of shortcomings in terms of the distance that they can cover, as well as other factors such as noise that might interfere with the signal. And so we have these modulation processes so that it can make up for that shortcoming of the natural wave.
All right. Good. So pretty much we learned from last week that we need to have modulation, which is, what is modulation again? Anybody can tell me? If somebody asks you,
the changes, from what I remember, it was the changes in the properties of a wave, whether it be via the phase, frequency, or amplitude.
You're getting there. It's not fully, but getting there. Anybody else want to add to so Stuart? So somebody should ask you, what is modulation? What is modulation? Modulation of a signal. What is modulation? How do you define modulation for somebody?
Sir, I would say like as a change. So like just like the change in the energy, sir.
Okay.
Sir, incorporating a message into a wave by changing one of the characteristics
All right, that's more like it, sir. We can. You see, remember something, guys. I said, guys, you know, ladies, you're guys as well, right? Guys, in terms of the class now. So don't think that I'm only speaking to the males. Remember what we're doing now. If you always think about it, almost every phase of what we're going to be doing, try and think and remember the analogy about the child going to school from half a tree to downtown or vice versa, right? On a packed bus at peak time. Good? So the child is the message. The child is the information that the child represent the message.
Sure,
in the aim wave.
So
go ahead.
The modulation is like a package.
You dropped out just now. I didn't hear you.
That could we say that modulation is a package that transport information?
Good. It is, but it's a little bit more than that. And follow where I'm going now. So here it is that you have information similarly to the baby that we're talking about going to school, right? That's the information. That information needs to be protected as it leaves the source heading to its destination. Because there's going to be the fear that the information will not reach in a form that even if it reaches, it will not be in a form that it was meant to reach the destination. It could be the case that it is so distorted that it provides either misinformation or no information. So you need to protect the information so that communication can be successful. Okay? So here it is that you have the information that you want to protect. Doesn't matter what type of transmission medium you're going to be using. You know that the probability of noise interfering with the signal is very, very possible. Hence, you want to protect it. So the parents know that the child is likely to encounter a hostile environment to the point where they might, be not only scared of going to school, but be physically harmed. Because, and sometimes it's not even deliberate, but because of the natural nature of how people are, right? Hence, for signal or for the information purpose in a communication system, we want to protect that information. We can protect 1, 2, 3 properties of the information. There are 3 main properties of information or any form of signal. It has an amplitude, it has a frequency, and it has a phase. Okay? So amplitude, if we choose to protect the amplitude of the signal, it means that we're choosing to perform amplitude modulation, because the modulation is a process of varying a higher frequency signal using or varying some property of a higher frequency signal using the information signal. So what's going to happen is we're good, and that's exactly what happens again if you think on the line of the child going to school. That parent or parents would have either gone to work or gone to or be busy doing something at home. But because of the fact that the parent or parents recognize that that child needs to be protected because of the transmission medium or the transportation medium in this case, that child has no cause, that parent or guardian, to do what? To modify their natural or the things that they would be doing naturally or normally. So it's the same thing as it relates to signal or as it relates to information. So this information signal, it wants to get safely from transmitter to receiver. So if a person recognizes that this individual, of this signal, the best way to get the information from sender to receiver is to protect the amplitude, because that's where the information, the main information is. Then they're going to use the amplitude of the information signal, or they're going to use the information signal actually, the complete information signal, to change the amplitude of a higher frequency signal. And that's why the higher frequency signal now has become the parents, because you know the parents would be like the bigger person, right? Or the guardian would be that bigger person carrying the child. So that parents' morning routine has been hampered or modified in lieu of aiding the child to get from home to school. So what you do, again, you put, for A modulation, you put a higher frequency, higher amplitude signal called a carrier, because that's what you want. You want a carrier to carry the information from source to destination. So the carrier, so you have a carrier wave that has higher amplitude, higher frequency, and that higher amplitude, higher frequency carrier wave, its properties are going to vary based on the modulating signal or the information. So the modulating the modulating signal or the information signal, they're the same. They're interchangeable in terms of speaking about amplitude modulation, all right? So you're using this signal to change the amplitude of this bigger signal called a carrier. So you're going to change the amplitude of the carrier based on the information signal. So let's again go back to the bus business with the parent there. So yes, Delroy.
So it's like you're imposing a signal onto the carrier wave with a view to protect the information then, or to ensure that the information gets to its destination.
Absolutely. Again, I was just about to say, it's like that parent. Let's say that that parent did not went to the bus. And we're talking about pre-COVID time. I'm assuming that that's not happening again where people are cramming in a bus. But that parent went onto the bus with the child. So right away, realize that the parent's normal routine has been changed, whether it be going to work or elsewhere because of the child. In addition to that, when the parent or guardian is on that transportation with the child, that parent guardian is going to do everything possible to protect the child. So it's like that parent is, even if not physically wrapping his or her arm around the child, they're trying to, take away any possibility of that child being harmed, by people around. So if the bus is going around a corner, or they have a, swinging from a pothole, and the other let's say standing passengers, swerve towards the child, what's gonna happen? What do you think the parents are gonna do? What do you think the parents is gonna do?
So they get in between the other person and the child.
Exactly. They're going to be trying their very best to ease that person from actually causing any harm to that child. So at the end of the bus ride, the parent might be battered and bruised, squeezed and, toes are stepped on and all that. Just because of the fact that they're protecting the child. What is the same thing the carrier is doing? The carrier now is a bigger signal, bigger in terms of frequency, bigger in terms of amplitude. And that carrier is going to do all its utmost best to protect the information along the transmission medium from noise. So what in amplitude modulation, what the carrier does is that it changes its own carrier, its own amplitude, sorry. It changes its amplitude just to protect the amplitude of the information signal. So now you're using the information signal to vary the amplitude of the carrier signal, while it's assumed that the frequency and phase of the carrier signal remain unchanged. Yes, sir?
I was saying, could you visualize it like a virus in getting into someone's body, like so the virus and the carrier would be the person, so the carrier now becomes the virus in a bigger sense, if you get what I'm saying.
Yes, sir.
We could have used a certain, sir. We could have used like an item. You buy an item online and you put in a parcel and you get it in the box, pen up, but item still all right.
All right. So that parcel would be like the carrier. It does everything to protect the absolute.
Get all the button.
Right. So that's the concept. That's what I want you guys to understand very clearly. And then it helps to shape everything else going forward. So in amplitude modulation, what you're doing, you're basically changing the amplitude of that, of that carrier to protect the amplitude of the information signal. So anyhow the information signal amplitude shape, the carrier is going to shape accordingly because it's doing what? It's doing its utmost best to protect the information.
So in that case, then, sir, it means then that the carrier wave is going to overlay the information signal.
All right. So I'm happy that you went there because this is exactly what we have sharing on screen that we're going to be looking at. No, everybody can see my screen?
Yes, sir.
I'm seeing the screen, but we're kind of filming up a D on glasses. which may not know, but maybe just go and work with this. Oh, wait, let me get disconnected or something. You know, buddy.
No, man, you're still here. I'm gonna start. I'm gonna start to move the screen. So just
You're not alone, man.
all right. So from what we're seeing, pretty much you can see the definition principle of amplitude modulation. Let me see if I can increase the size of this. I heard Mr. Freighter complaining. I don't want to leave anybody with a blind eye. All right, so you guys are seeing what I'm highlighting?
Yeah.
All right, so right here, it speaks to the concept of what I just mentioned. You see, it said amplitude modulation is the process of changing the amplitude of a relatively high frequency signal in proportion with the instantaneous value of the modulating signal. Or the modulating signal is what I said is called your information, right? So the information is what you want. You're changing the amplitude. You're changing the amplitude in regards to the of the higher frequency signal in regards to, so that my highlight is kind of messy. So, but that's what I want you to see first and foremost. Now, how do you go about doing the whole concept? So somebody, before we even get to, so somebody was saying, so this is the picture of what we just spoke about, ladies and gentlemen. Here, you will notice that you have the first wave is your information. That is what you want to get from point A to point B, all right? Are you with me?
Yeah, man.
Yes, sir.
Yes, sir.
Yes, man.
Good. But we know that if we send this information as it is right now over the transmission medium, it is going to be more likely it's so affected that the information might not reach to its destination. So the information signal, it has an amplitude, it has a frequency. So from peak, from peak to peak, the time and frequency is 1/t, right? So we can find the frequency of this model information signal. Obviously, this would be a carrier. So the carrier is a higher frequency signal, and usually it's a higher amplitude signal as well. So notice that the frequency here is much higher than the frequency here, because we're having, let's start at this point. We're having 1, 2, 3. We're having 3, and let's finish it. 4, 5, 6. We're having 6 cycles. Within 6 cycles, within the same time it will take for us to have 1 cycle for the information signal. So the information signal goes from here, well, it's not 6, but yeah, it goes from here to here. That's 1 cycle. If you look at it here, you see it's going to take 1, so 1, 2, 3, 4, 5, 6 cycles. So it means that right here, the carrier frequency, if you see here FC, the carrier frequency is much higher than the information frequency. That's any better now, Sofreta?
Yeah, man.
Try to increase the amplitude. The amplitude. All right. So what did we say that the information signal is doing?
Changing the amplitude of the carrier signal.
Right. And as you can imagine, the only reason why the amplitude of the carrier signal is going to change is because the carrier is moving to protect the information. So if the information signal goes high, the carrier is going to also go high to protect it, right? If it goes low, it's going to also go low in order to protect the information. And that's why we have this particular pitch here as the amplitude modulated wave. So if you should check the frequency, so the same amount of cycles per second for the carrier wave will remain. But what happened? The carrier amplitude, as soon as the amplitude of the information signal goes high, the carrier amplitude goes even higher, just to make sure it protects. So the carrier actually does move as per the information signal. So if you notice here, the outside here of the information signal, right here is actually the same as it is right here on the amplitude modulated wave. Everybody can see that?
Yes, sir.
Good. But whatever is happening here is happening also on this side, because they want full coverage and full protection. So you're just not protecting the information on this side. They want to protect it also, just in case on the other side, which is down here, so it has the same looking wave, but opposite in terms of its amplitude. So here is the unmodulated part of the signal. So nothing happens here, but as soon as you mix this signal or the information with the carrier, things start to change, and a change in direct proportionality to the amplitude of the information signal. And that's pretty much the detail. Yes.
The carrier signal is what's supposed to protect the information signal, right?
Yeah.
Yeah. From a layman's standpoint, one would expect the other way around, not the information signal envelope the carrier signal, but the carrier signal envelope the information signal, because that's what the carrier signal does, is to protect the information signal. I don't know if you understand the standpoint from which I'm arguing.
It's not arguing at all. You're making a point, but what we're saying, and think about it, and that's why I said always think about this analogy that I've used when you're talking about communication system. Just think about a child going on the bus. I just use.
So the carrier signal would be the parent.
The carrier is the parent, yes.
Yeah, and the information would be the child.
Right.
But look what we see happening now based on the diagram that you're showing, the lower one.
It's like a child, like a parent.
Is it like the child protecting the parent?
No. What is happening is that any movement the information makes, the carrier makes that in order to provide that protection.
Understood, sir.
You know what I'm saying? So if somebody,
yes,
so that's why I use the analogy that if the bus rock and the person's, rock to the left as well, it rock from a pothole or whatever, and person's rock, they're gonna go boom and rock on the baby. So guess what? The parent is gonna make sure do what? Put up that resistance to encounter that rock, If the child also rocks, so now this is a child now. So if a child rocking the bus, the parent is gonna go boom and do everything. You don't want a child to get, hurt by hitting the rail or hitting the seat handle or hitting another person. And so the parent is gonna go boom, move to anyhow the child moves, the parent is gonna move accordingly. That's why it looks like it's the child protecting the parents. But that's all. Remember, no.
Looking at it visually.
Let me explain the what you're seeing happening is because of every movement. It's not like the information is on the outside here though. And we're just saying that information is inside here now. It's inside. It's just that the carrier has reshaped its amplitude to match that of the information, only because it wants to protect it. So in other words, he doesn't want, and we're going to use some examples. Let's say that, the amplitude of the information signal at its max is 10 volts. And the carrier amplitude was 8 volts at its max, at its peak. Would the carrier be doing a good job protecting the amplitude of the information?
No.
Okay. So that's what happened now. The carrier, it does not go only, if you notice, just look at the wave. I think that's one thing you're missing. If we look in this diagram, let's say that the carrier amplitude is 10 volts and the information carrier is 5 volts. When you look here, what do you think you'll be getting? 10 volts or 5 volts? In terms of the speed, what do you think you'll be getting?
10, sir.
You'll be getting 10 plus the 5. You know why? You notice that this goes higher than here. Notice that right here? The resultant amplitude modulated wave, the amplitude of the resultant wave, for every part of the amplitude where the information goes high, the carrier amplitude goes even higher. So the carrier initial amplitude right here probably is 10. And if the information amplitude is 5, then the resultant amplitude modulated wave amplitude is going to be that 10 plus the 5 for cushion for the child, because you're making sure that you are reinforcing yourself to protect the child, that that child will never be. You have so much and super extra to protect the child. So when the noise come hitting, the noise is just hitting. You see this, the outskirt here, what we call envelope. Here are just the boundaries that the carrier has changed itself, yeah, in order to protect the information as the information changes. So as the information is changing, the carrier is changing itself just as much. So it's not like the carrier, yes?
Oh, you can finish, sir. I was just going to make an analogy or be used to understand it, know that you start explaining it.
Right, right. So I'm saying here, it's not like the carrier is just saying, okay, I'm remaining. The carrier amplitude is not remaining at, you notice right here, look at right here and right here. The carrier amplitude is the same right here and right here. But when the wave is amplitude modulated, does the amplitude remain the same for the carrier?
No.
Oh, the carrier amplitude gets bigger. So it's not only protecting now the 5 volt that I mentioned before, but it gets bigger to ensure that it does protect that 5 volt for the information signal by making itself now 15 volts altogether. So again, in a scenario of the bus, the child is in the bus. The bus basically made that, so everybody was standing up, for argument's sake, holding on. The bus has made that swerve. That parent, in order to protect the child, you think that parent is going to stay relaxed and easy at the same, in the same demeanor as how he or she was before that the bus actually made that swerve?
The parent is going to always adjust himself or herself with a view to protect the child. Anywhere, any curve or any way the bus jerk.
And that's
exactly, the parent.
Right.
That's exactly what is happening here. So the parent is now making him or herself bigger in order to cushion that change that the child would have experienced. Or in this case,
it means then, sir, that the carrier would have had that degree of flexibility to adjust itself accordingly based on what is happening to the information wave.
And that degree of flexibility is what we call amplitude modulation. That's what we're talking about.
Right.
The flexibility is what is the result of amplitude modulation. And if you're talking about frequency, it's the same thing. The carrier has that no flexibility to change its frequency in order to protect the information. And when it comes to phase, it's the same thing. The carrier is going to change its phase orientation in order, in lieu with the change in the information signal, just to ensure that it does everything it can to protect the information. And that's what modulation is all about. That's what I want to get you guys to understand. That a carrier is the one that changes. The information, you don't want information to change, because you want information to remain intact to go from point A to point B. It's the carrier that is changing. It's the same thing I mentioned before. The parents or that parent or guardian would have been at home or at work. But because of the fact that he or she has to now follow the child to go on the bus, they are changing. It's not the child who's changing now. It's the parents who is now, our guardian, who's now changing.
With a view to protect the child.
Exactly. And that's what, from a layman perspective, is modulation. And how does it, for amplitude modulation, how does it the carrier change? The carrier changes its amplitude in relation to the change in the amplitude of the information signal. And if it was frequency, the carrier would change its frequency due to the change in the amplitude of the information signal. So we're going to look at the FM a little later. We just wanted you to understand the concept that we have here. Now, there's something that is also important about this diagram, ladies and gentlemen. And that is, as I said before, you're not only changing that, the carrier is not only changing in terms of, because, you know, if it's a, excuse me, if it's a continuous signal, the signal is going to vary between plus and minus values for its peak, right? So it would be foolhardy for the carrier to only be protected or protecting just the positive amplitude of the information signal. So it has to protect. So any change that happens on the positive side, equal change happens on the negative side. Okay? So what happened is that the information now is all engulfed in here, all of here, and going so that it can travel from point A to point B, with the carrier being its light and shining armor protecting it. In this process,
that's the reason the carrier signal has to be of a higher amplitude than the
absolutely
and the information, because then when it reaches like the negative value, then you would have a problem, because how would you protect it if the negative amplitude is greater?
Also, let's think about it this way. If the parent is only protecting a child if the bus swerve right and don't protect the child if the bus swerves left, it means that that child is not fully protected. Agree?
Understood.
Yes, sir.
And that's exactly what's happening here. It's protecting, right? So it's protecting when the information is positive and when the information is negative. And that's why we have the information inside here and the carrier. These are what are called envelopes that forms, and these envelopes have been formed only because of the fact that the amplitude of the information signal is causing the carrier amplitude to change. So all of this is a carrier amplitude, you know, it's a carrier amplitude. But because the carrier amplitude is varied with the information signal, you can be rest assured that information will be relatively safe within the envelopes of the now amplitude modulated wave. Now that has happened, what we have three things that has occurred. As you can see in this diagram, we're going to have the carrier still existing. It's just that its amplitude is going up and down based on the information signal, yeah? So this is a carrier wave still, right? Somewhere inside there. Agree?
Yes, sir.
Good. But we also have two other things. We have an envelope that forms on the top half of the no modulated AM wave, and also bottom half of the amplitude modulated wave, which is going to cause some changes in the overall spectrum of the wave. The thing though, gentlemen and ladies, that we need to understand, as I mentioned last week, what I should probably ask you guys as a reminder, when a parent reaches school at the school gate, is that parent needed anymore at that time?
Nope.
No, not at all. Mission accomplished, for at least for that time, eh? So,
Right.
Yes, because the information would have got to its destination.
Exactly. So what do we do with the carrier?
We need to now demodulate it.
We need to get rid of the carrier. Because the carrier has done its job. It has no other purpose, no use. Agree? No other use. It has done its purpose by protecting a child or protecting information from source to destination. It's the information that we're interested in, not the carrier. Agree?
True.
Yes, sir.
Right. So this is the thing now. We don't need to get rid of the carrier. But as you can see in this diagram, it's not only the carrier that we have, but we have two sidebands. Our two side, see, one is on this of the envelope and one is on this side of the envelope. Okay? And that's called the lower. Here would be your lower sideband and the upper sideband, which we're going to get into a little bit more when we look at the frequency of a signal. Now, here is an example of amplitude modulation and modulated wave 4.2. Well, now we're looking specifically at the frequency. What we saw before was what we call a double sideband full carrier signal wave, which is this double sideband. We can see the two sides, right?
Yeah, man.
So it's a double sideband and a full carrier is inside here. So we call it a double sideband full carrier amplitude modulated wave. Okay. Ideally, the frequency of the modulating signal of the carrier signal is not supposed to change. But there are some changes, of course. Now, what I want to do is to get into the mathematics of things, because you can actually read through all of this and know why and see how we do the calculation. Let's look at how we came with the change in frequency, and let's see how the frequency actually affects anything. And we can actually jump straight to the whole concept of how mathematically the amplitude modulated wave has occurred. So that we'll do in this section. So I want you guys to follow me carefully now. So we have two waves. We have a carrier wave, and the general expression for a wave or a signal is the instantaneous value of that signal is a peak value of the signal, sine or cosine 2 pi f for the frequency of the signal, and t ft, because you know that is a angular rotation, right? The signal actually goes through 360 degrees, which is why it is actually a frequency, because it goes through different time intervals and it starts all over. It becomes cyclic, right? So generally, we should all know this. We should all know this, that any wave, any sinusoidal wave, be it cos wave or sine wave, can be expressed in this format. Agree? Where in this case, VCT is the instantaneous value. So if we have a wave looking like this, oops, and pardon my drawing. So if we have a wave looking like this, we're saying that this is time versus what?
Voltage.
right, our magnitude, right? Time versus amplitude. And in this case, amplitude of the signal is voltage, right?
Yes, sir.
The amplitude versus time. We're saying for different interval of times, for different intervals, you realize that, so if this is T1, so it's T1, T1, T2, etc., etc. We're saying that for every interval of time, the amplitude has a particular value, different value. That's why this is an analog signal. With a digital signal, that would not be the case. I know all you bright students from digital electronics who know that, right? So if we take the amplitude of the signal at time t, that's what this t is. The instantaneous value of the signal at time t will always be this, meaning that it will have an amplitude that is that is a sinusoidal wave, right? Are we clear on that?
Yes, sir.
Yes, sir.
Yes, sir.
It's just a simple expression of the instantaneous value of a signal, right? Now let's say that this is the instantaneous value of the carrier signal. Okay, so this is a carrier signal when it was not modulated, nothing happened to it. Then comes the information signal. And what is the information signal going to do? The information signal is going to, for amplitude modulation, is going to change what? The amplitude of this carrier signal. So it will still be a carrier signal, a sine, whatever. But what's going to change at different interval is your amplitude. Agree?
Yes, sir.
So the
Yeah, because they're not
amplitude,
at the same level.
right? So we could say then, okay, for amplitude modulated wave, all right, even before we go this, let's say, so this is for the carrier wave. The information wave, and let's call it VM, for modulating signal, modulating. So let's say this is VM. VM of T, because remember we have a carrier wave information signal to know. So VM of T, how would we express that signal? Since we know how to express a carrier signal, how would we express the information signal?
So it'll be e to the m sine 2 pi f mt.
Only EM, which stands for
Yes,
the peak magnitude of the FM, right? So it will do EM
right.
sine. Hey, Dre. This works. Uh-oh. Uh-oh. Undo this.
To change it, but no, wait, that's the so that's the eraser.
I know. So I can't draw it?
No, you can't touch the screen while you're drawing it.
Doesn't work.
Because it's still on the eraser.
No, it doesn't work. It's all the work in there. So it'd be so nice and comfy if I had that. Yeah. So be EM sine, and forgive me again, I'm trying to use my sine open bracket 2 pi f of m, because that's now the frequency of the modulating signal, t. So that's what but everybody can make out that?
Yes, sir.
My markers are working too well.
Yes, look like a 5, but going back to the recording, one would understand what you're actually doing.
All right, so this is a S. Okay. That's more like it.
Yeah, man.
All right, and this is so this is the information signal. All right, so what we're doing now, we're using the entire information signal, yeah, to change the amplitude of the carrier. So what we're doing is we're basically adding this one here. Let me choose a different color. We're using all of this now, which is a carrier. That is going to act on this. That's going to cause, all of this is going to cause the carrier signal to change, because this is the information signal now. So this information signal is going to change the carrier signal. But in particular, what is going to change? It's not going to change the frequency. It's not going to change the phase. It's going to change what?
The amplitude.
The amplitude.
The amplitude.
So,
Okay.
sir, I have a question. Would the VMT at a particular point, I know that what the VMT we're calculating is the voltage at a particular time. So would the VMT replace the EC?
No.
Oh.
VMT is not replacing the EC. The VMT, yeah, that's what I'm saying. That's why I had this, all of this, which is VMT, is going to, if you remember the diagram up above, we're saying that the information signal, the child. So this is the child. Yeah? Or the information. So you want to protect all of this. So you're going to protect all of this.
So that is going to be imposed.
Right. So you're taking right. You're going to take all of this information. Yeah?
Yeah.
And that information, it's the amplitude of this entire carrier signal that is going to be affected. That's why it's called amplitude modulation. So it's the amplitude that is affected, not the frequency, not the phase, which is here, but it's the amplitude. And that's why we have this equation. That's next. That the instantaneous amplitude of an amplitude modulated wave is equal to EC. So you see EC back here, right? So is that EC, yeah? Mm-hmm. Plus, so all of this is what's affecting what? EC, all of it, you realize? All of this is what's here. That's what is affecting. It's affecting what? The amplitude. So that's why it's added to the amplitude of EC, of the carrier wave, eh? Not to the frequency, but of course the wave isn't finished because it still has this part now still represent different color. Still represent what?
Index.
So this part is still a carrier. That's what makes the carrier is varying, you know. So that's the frequency of the carrier, frequency and phase. Phase is 0. But that's the frequency of the carrier. And this is the amplitude of the carrier. So that's the amplitude of the carrier. But we do it this way specifically because we want to show you that it is all of the information signal, which is all of this, that affects only the carrier. So it's a carrier that is now fixing itself, the carrier amplitude, that's fixing itself to protect the entire information signal. You get it? It's the entire amplitude of the carrier signal that is flexing it and fixing itself so that it protects all of the information. So we're not saying that only carrier exists, because the carrier still has its frequency. See it right here? But we don't want it to get lost that the information signal is affecting the carrier frequency. The information signal in AM is only affecting the
Amplitude, sir.
The amplitude of the carrier signal.
Sir.
Yes, sir.
So when there's noise, what part of the equation is changed? Or
what part of the equation has changed?
Mm-hmm.
All right. That is just an expression. That expression now mathematically is going to have to be dissected. So that's not an expression. I just have the expression there for you to see clearly, because that's what I want. I want you to get it clearly. So we'll go on and move to frequency modulation and so on. You know what I'm talking. So if it was frequency modulation that we're doing, ladies and gentlemen, we would not have put this, all of the information signal over here. We'd have put it over here to affect the frequency, agree? And not the amplitude.
Makes sense.
Good.
Sir, but noise.
Right.
Noise changes the underlying. When you get noise on your signal and it corrupts it, wouldn't it be changing one of the values in the underlying function, basically?
Okay. Noise is going to affect everything. Frequency, amplitude. But noise usually affects amplitude more than anything else.
The amplitude.
And there's a very simple reason for that. If I'm talking right now and something is knocking, or let's say I turn up the television, or there's a heavy duty construction that is going on, you realize that is the amplitude of those things would be superimposing on my amplitude and creating that noise challenge, right?
Yes, sir.
And that's because the amplitude of noise is so easy to superimpose on the amplitude of information. The frequency, not so much, but amplitude. And that's one of the first things that people who design communication system recognize, that noise, its amplitude. So let's do some form of modulation to change the amplitude. But afterwards, I realize that, we can not only change amplitude, we can change other things. Let's see how it works. And we'll learn that a little later. So let's jump into the mathematics of this. So everybody understand what I'm doing now? I can clear this, I can wipe off this part. Look at here, not wipe off.
Yeah, you can.
Sorry. So, mathematically, this is a trig identity. So, you guys remember high school or first year mathematics, where I did trig functions as a part of our math class?
Yes, sir.
Okay, let's hope so, because I drop asleep. We don't want you to just learn a thing and pass the course and move on. There's a reason why we want you guys to be learning the things from previous class, and that's because of the fact that we want you to be able to transfer knowledge. So here, we actually can rearrange this equation right? To look like this. But before I get to here, what I need to tell you is that when you superimpose the modulating signal, sorry, amplitude on the modulating signal onto the amplitude of the carrier, you recognize that there's a change from the previous diagram that I showed you, right? With the two sidebands, right? So you realize that when you superimpose them, what happens is that the signal amplitude becomes larger or smaller based on the signal itself, right? No. Good. Now, the thing that affects the level of modulation and how well the signal is modulated or not modulated is what is called a modulation index. And it's normally known or is written as lower script m. The modulation index m, if you can see that, nope, that's not a good color to use there. Yes, let's use this. So M, which is known as your modulation index, I actually can go back earlier to show you, to give you a better idea what I'm talking about.
Your pause already.
Okay. Here, modulation index or coefficient of modulation is a term used to describe the amount of amplitude change present in an AM wave. So how much does the AM wave changes from its original value, peak value, which is EM, which is EC, sorry. How much is it changing? And the changes that it undergoes is fully dependent upon the peak of the modulating signal or the information signal amplitude. Because remember I said that if the bus rock in a particular way, the parents want to rock just as much or even more just to make sure they protect the child, right? So
yeah, man, because it's the information signal is going to determine
the amount of. So let's put it this way, because I want you guys to understand the concept. So the amount of rock that the child, that the mother or the parent or the guardian or the rock in that bus is dependent on how much it takes to protect the amount of rock that the child would undergo, or the amount of rock that other people would have performed in order, or would have undergone as well in order to affect the child. So modulation index is the amount of change the carrier signal amplitude has undergone to protect this information signal amplitude. So modulation index in a nutshell mathematically can be expressed in this way, in that the amount of change
is the coefficient of modulation. Is you refer to as the modulation index?
It's the same thing. It's the same thing. Modulation index, coefficient of modulation. Undo. Coefficient of modulation speaks of percentage, right? The percentage modulation. Here, for a modulated wave, this is what modulation index is. So, how much change will the carrier change? Depends on how much change the information signal amplitude had changed for amplitude modulation. So it is a ratio of the information signal peak amplitude to the carrier peak amplitude. Okay? So,
If,
for example,
10 times, that means that the carrier is going to change 10 times too.
Yeah, if, for example, I mentioned before that the peak amplitude of the carrier was 10 volts. That is before it has changed.
Yes, sir.
And how much did I say the information?
5.
I think I hit 5.
Okay. So therefore, what will be your modulation index? What will be
0.5. 0.5.
Okay. So what this value mean is that the carrier is going to change by 50% in order to accommodate amplitude modulation to protect the information signal. All right. So this actually is a percentage. So it's a percent modulation. Percent modulation is the modulating index or the modulation or the coefficient of modulation times 100. Right? That's what percent modulation is. How much percent will the carrier change will the carrier amplitude change in order to protect the information signal? And it's a measure of the information signal amplitude, peak amplitude, over the modulation signal, peak amplitude. Am I clear?
Yes, sir. But you know what I'm saying though, sir, when them say parent overprotection is never good. Yes, sir. Overprotective parents, sir, never good.
Some children will disagree with that.
But you're supposed to know me, I get that still, sir, once I hear me say that.
Yeah.
A lot of things say that, sir, because it kind of give avenue to like another part of the analogy in the sense that overprotecting information
We're gonna get there.
be okay, all right, cool.
We're gonna get there. I know exactly what it is. We're gonna get there. All right. A matter of fact, right now we can look at it. If for example, the modulation, the information signal amplitude was 10. I alluded to that before. Let's say in one case, in a case, say EM was 10 and EC was also 10. So EM was 10. I'm talking about voltage here now, right? Because there's a peak voltage, and EC is also 10. So EM and EC, both 10 volts. What would be your modulation index or your coefficient of modulation?
1.
1. Okay. And what would be your percent modulation?
100%.
100%.
Percent M would be this times 1, right? Times 100. Oops. Times 100. Now this is the only time, or this is one of the only time that 100% is not good. Why?
sir,
They
because
don't really have much cushion, sir.
Exactly. In this case, what you're saying is the carrier amplitude is the same amplitude as the
The information.
So it's not protecting it at all. Anything that hits the carrier hits the information. So what happened in a case like that is that you're not protecting the modulation. So we would be having a nice curve as what we had before, like in this. We'll be basically having a flat thing going all the way like that, right? There'll be no curves. No. So that's good. So what it means is that as soon as boom, 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 noise hits the envelope, it is affecting the carrier just as much as it's affecting the information. So in this case, the information is hidden inside here. So as soon as the noise hits here, it will be hitting the carrier. The carrier is taken care of. So again, going back to the analogy of the child, it's like the child is pretty much the same, has the same strength. The parents really don't have no much more strength than the child.
Right.
So anybody who is hitting the child or hitting the parents, the parents is not even bracing to protect the child. It's basically affecting the child just as much. So that's one of the cases when the modulation index is 100, it's not a good thing. It could even get worse. It could be a case where EM is greater than EC. And if EM is greater than EC, then it means that the modulation index obviously is no good because, the level of protection for your AM wave would not be of any
Job protecting the parent at that point.
Exactly. That is the case though, where the child seeking to be protected would not be protecting the parent. And therefore, any challenges
that means the information are exposed then, sir.
Very much so. That's exactly what it means. The information will be super exposed. So the whole process of amplitude modulation, in that case, would not even be necessary. You would only be utilizing equipment, power, time, without really forming any form of protection. So obviously, if we have this equation here, we could actually do a transposition as we have done here. If we want to find from here the amplitude of, let's say we know the modulation index and we know the amplitude of the carrier, we could find what the amplitude of the information signal is. And vice versa, if we know the modulation index and we know the amplitude of the information signal, then we could find the new amplitude of the carrier signal. And as I mentioned before, percent modulation for AM, because it's different for FM. Percentage modulation for AM.
Sir, I still don't understand what you just do a while ago. It said if it was one, EM is the peak change in amplitude, right?
EM?
Yeah.
EM is the amplitude, the peak amplitude of the information. That's what EM is. It's a peak amplitude of the information. EC is the peak amplitude of the carrier.
If it is one, that means that the EC had to change amplitude. It had to double, right? Because when it was 50%, it was half as it changed by half. But when it's 100, it doubles, right?
If you need to fix the question.
No, but if you look at it from the
Hold on.
50% is half, so 100%.
Hold on. Let him.
Or 200%.
Okay. So So ask yourself a question again and think about it. Think about it while you're asking this. Because this is why I give you all the analogy. So here it is that the carrier wave amplitude is supposed to protect the information wave amplitude. Agree?
Yeah.
Okay.
Because
If the information amplitude and the carrier amplitude are the same, it means that the information signal amplitude could not be carried or could not be covered by the amplitude of the carrier. It's not being submerged, it's not protecting, it's not forming that envelope.
Sir, what does EM equals 0 mean?
EM
equals 0.
If EM is 0, then it means that you don't have a signal. Because if EM is 0, it simply means that your modulating signal doesn't have a voltage, a peak voltage. Remember, mathematically, what we're saying is V. Hold on.
Prime price, sir.
VM of T.
The prime price is something there. The prime price is the information which is off the side of the carrier.
Right. We're getting there, man. Let him ask a question. I want anybody to be free to ask questions, because that's where we get a chance to clarify this stuff, okay? Remember that VM is the instantaneous amplitude of your modulating, so of your signal. So your signal that you want to send, it's going to change. It's going to change amplitude of different interval of time. But that can be expressed as EM, where this is a peak amplitude, EM sine.
Sir,
or
what
plus.
I'm seeing here says that EM isn't necessarily the message, the information signal. It's how much the carrier changes to protect the child, basically. That's what I'm seeing.
EM?
Peak. Yeah, it says peak change in amplitude of the output waveform voltage.
No, man. That's after modulation.
That it's right there.
Right.
That would be after modulation.
No, but we're not. No. Look. Okay.
Right. I don't word they may look for. Me know what you were saying with the EM equal the information of the input wave. Waveform. But
right.
This is saying output waveform. Okay. I think either the notes wrong or you say something wrong, right?
No man. That's follow. What output are they talking about? What output?
The entire modulated.
No, that's the thing. It's a peak amplitude in the amplitude of the output waveform voltage. This, what I'm talking about here, output waveform, this is the output to go to the transmission medium. The output. So this is
it would be the output of the transmitter.
Output of the transmitter, exactly. So that's the output of the transmitter. That's what you need to send. But you can't send the output of the transmitter into the transmission medium without it being protected.
Okay.
You follow me? So don't get mixed up with the terms, all right?
Yeah. On the diagram I was looking at, says input, the input would be the message and the output would be the enveloped.
So when we look at the transmitter generally looks like this. This is the transmission medium that you want to go out on, right? If we send the information, so this is the information that is coming into the carrier, into the transmitter. If we send that information out, so we just use it, and we did this last week. If we just use a transmitter, remember one of the purpose of the transmitter is to convert the information to an appropriate form suitable for the transmission medium. Remember that?
Yeah.
Good. So if we have the information, we just put it in a transmitter just to make it suitable for transmission. What's going to happen is that once it hits the transmission medium, all it broke loose. And we know that already. We know it's going to be susceptible to noise. So what is done is that this is the information signal, which is VM. And because it's changing with time, VM of T. So that's the information going into the transmitter, which is going to be, so this is information that is in the transmitter without being transmitted. So if it's without being modulated, rather. So if that's the case, this is what EM, this would be EM sine, bracket FT 2
pi FT, or you can say omega T.
Right. 2 pi FT, right? 2 pi FT. Okay? So that's what we have. All that would have happened coming out here, that would be the output. This is exactly what would be coming out here into the transmission medium. All that the transmitter would do, I'll call this TM for transmitter, TX. All the transmitter would do in that case is just basically make sure that if the information was in the form of text, so text message cannot be transmitted, for example, to free space or even over coaxial cable or fiber optics cable as is. So the transmitter in that case, all it will do is just do the appropriate conversion so that it can go out over the suitable medium. But what we know is that if that happens, so that this is what will be coming out, conditional coming out. But we know that that is the case, all hell broke loose when noise hits it. So what happened is this. That carrier wave, so this now is a carrier wave, which would be VC of T. VC of T, which is expressed earlier. We know how to express that. That goes into the transmitter, and it's mixed. So we call this a mixer. It's mixed with the information signal through the process of modulation to change some property of this wave, this carrier wave VC, some property, whether it be frequency, phase, or amplitude, to give you now a VAM of T. So that's what is coming out after these two are mixed. And VAM of T for amplitude modulation, we just show you down here what that equals to. That equals to changing the amplitude of the carrier wave with the entire information signal. Now what we're saying is, if the amplitude of the information signal and the amplitude of the carrier wave signal are the same, then what happens is that from an amplitude modulation perspective, really and truly, you're not protecting the amplitude of the, remember, this is what we need to protect. If you're using amplitude modulation and the amplitudes are the same, you're not protecting it. There's no way that you are engulfing it or protecting it from nothing. That's why when EC equals to EM, the wave is not protected if amplitude modulation is what is being undertaken. It's not being protected because the amplitudes are the same. If, and that's how we know that your modulation index have a lot to do with how much you protect the information signal with the carrier. Because, as I said before, up here, if you look, it's the coefficient of modulation, which is also known as the modulation index, is a term used to describe the amount of amplitude change present in the amplitude modulated wave. It's to describe the amount of amplitude change. Of what? What amplitude? Whose amplitude is changing when you do AM wave?
The carrier.
The carrier. So it's the amount of changes that the carrier amplitude is will
If
go
the two
undergo.
amplitudes are the same, wouldn't the carrier just double and then it's base the entire
No.
If the two amplitudes are the same,
Uh-huh.
right? Cool. That means the carrier would go and extend to twice its size to reach the peak amplitude of the information. But then the frequency, both of them would have different frequency, and based on the time, it would vary, right?
Okay.
Because they have different 2 pi ft. So why is it a problem if the amplitudes are the same?
All right, let's go back at this.
Look at it again, because
hold on. Let's relax.
May I struggle.
Hold on, relax. Look at this.
First time in a long time, may I struggle to understand something.
Wow. Well, look at this.
First time.
Look at this. All right. So here,
yes.
Let me erase all of this part. This is actually very easy because I guess you're looking at it on one way. Let's look at it this way.
Wait, could I attempt something, sir?
Yeah, go ahead. Color.
I was saying, Travis, there's a difference between modulation and superimposition. You're thinking about simply adding the two waves, like when you're doing, when you're superimposing the two waves, superposition, but it's not the same thing. So in superposition, if you have two amplitudes, you simply add the amplitudes together and so on, but it's not necessarily the same thing.
We're talking about the peak amplitude.
Yes. So what you're saying is if you have a wave, so if you look at the carrier wave that he has right now, the carrier wave, let's just say that
there's an easy way.
Information signal has the same amplitude. You're thinking that because we're trying to protect it, you just simply add the two amplitudes together to make a new wave.
Yeah,
I'm saying that's not that.
You're perfectly right, but hold on. Let us help him here. Let us help him here. Work with me now. Was it Travis?
Yes, I'm here.
Right, you're here.
So
yes, hold on, man. Don't ask any question. Look how I'm do writing, and tell me now when you don't follow. All right. So right here, this list right here, or anywhere along here, this is VC plus VM, right? Agree?
Yeah.
And that's why you're saying, oh, nice. That would be, 10 plus 10, right?
Sure.
Good. Let's look at here now. Because remember, it makes no sense for the parent to be protecting the child in one direction, right? Let's look at what happens here. What happened here is minus VC minus VM, right? Right here, because it's on the negative side, agree?
Yeah.
Okay.
So
so this would be minus 20 in that case, right?
Yeah.
Okay. Let's look at the signal now. When noise is really going to affect it.
So is the the diagram wrong? Wait, is the diagram wrong? Should the wave be over the messenger wave? Like, should the carrier be overlapping, like crossing past that line? Technically.
Let me see. VCM plus VC.
Sir, we can answer more, sir.
Well, maths is gonna help him out right now, man. VC plus. Right here, you agree that at this point it will be VC minus VC plus VM, right?
Yeah.
Okay. All right. So what happens here? Mathematically.
What happens here?
Emma, you're using numbers. Is that going to be minus 10 plus what?
10.
Okay. So what would be the amplitude of the modulated wave at that point?
0. 0.
0. Okay.
Yeah.
Is amplitude modulation happening at that time?
No.
Okay. So what can you say from that?
That's wrong. That's very wrong. All right.
What is wrong?
The wave, the information is gone, is lost.
Okay. And therefore there's no modulation that is taking place because you have lost your information. Not true?
Yes.
So that's the point. That's the point that I'm saying. You do not want to have a case where the information signal and the modulating signal amplitude are the same, or the information signal amplitude is greater than the modulating signal amplitude. Because what's going to happen is that at some point in time during the process, amplitude modulation and then transmission, the signal is either going to be lost or it's going to be totally exposed to the elements that you're trying to protect it from in any case in the first place. So that's why it is never good to have both being equal. It might look nice when the signals are equal. Look nice. It doesn't look so nice when they're equal and opposite, because you lose your signal at that point in time where you need to protect your signal. Once information is lost in a communication path, it is sometimes lost forever. Think about a commander sending a message to his troop in battle. And believe it or not, amplitude modulation is still one of the most used method of communication in the army because of the distance that the signal can actually transmit. It transmits, we spoke about this earlier, over longer distances, around mountains, around objects, than going and trying to penetrate objects, and then objects are great enough that it totally cancels the signal. So that's why you still should use amplitude modulation. But you think about it. When the signal is canceling out each other, the general just sent a message to the troop to retreat because the new information has evolved that they're in imminent danger. But your signal at that point in time, because the amplitude of the modulating signal and the amplitude of the information signal and the amplitude of the carrier signal are actually the same. At that point in time, the information get lost. What happened next is catastrophe. So that's one of the reasons. That's one of the reasons you never ever want this to happen.
Yeah. If we never go through this, I wouldn't even think about that situation with the signal being gone completely.
All right. So look better now.
Yes, thank you. You know, right. Sorry for waste 15 minutes.
Nah, man. It's a learning process, boss. It's a learning process. That's what I'm here for. Because most of the other stuff, that's here I'm talking about. You can read it. I'm just gonna go through the difficult things and the questions that you have. Good?
Yeah.
All right. So here we are. A matter of fact, it's all of this. Is it what I just explained? Travis,
Yeah.
that was Travis, right?
Yeah.
It's actually covered right here.
Okay.
Vmax equal to minus VC minus VS. All that is explained right here. Okay? All right, going back to what we're trying to get at. We're saying then that the modulation index is this. Oh, I'm sorry, not this. Modulation index is this, right here. And we can actually change the subject of formula to find any one of the variables we want. Agree?
Yes, sir.
Good. So if we want to express EM, we can say EM equals the modulation index times the amplitude of the carrier. Now, always remember, ladies and gentlemen, that for proper modulation, your modulation index is going to be less, it's going to be a fraction. It's going to always be less than 1. Once you see a modulation index is 1 or more, then amplitude modulation is not going to be a good choice of modulation to protect your information. All right, so once we know this, we can jump to back where I want you two guys to go for tonight. So this is our lower amplitude modulated wave in terms of an expression. But from a mathematical perspective, we could actually write this same equation like this. Agree? Because if you look at this, we could write EM in the form of EC from what we just learned a while ago. That EC actually equals EM actually equals MEC, right? This right here actually is what? EM. Everybody remember how I get this?
Yes, sir, by transposing the formula for modulation coefficients.
Excellent. All right, and if that's the case, we can do some factoring. Agree? Because we can factor out the EC, which is what we get here. So if you factor out EC, you're going to have EC into 1 plus M sine blah, blah, blah. Agree? And then we just take that EC that we factor out in front of everything and appropriately put it here, because at any rate, it was going to be multiplying. If it wasn't here, it'd still be multiplying everything. So it's not a problem to put the EC right here, mathematically. Following me?
Sir, is it that why they couldn't factor out up to the 2 pi f for frequencies? Is it that the frequency
look at this. The frequency here is different from here. So you can't touch the angular frequency any at all because they're different. You understand me?
Okay, sir.
The frequency are different. So you can't say sine, you can't factor out a sine because of frequency. It's a sign that's going to change it.
Oh, yeah, that's true. Yeah,
right?
sir.
Good. Mathematically, we're sticking to our guns, what we know. So here, what we have, and I'm going to wrap up shortly, here, what we have is this expression. But do you notice something? Ladies and gentlemen, you realize that this, due to right now how it is written, is showing us clearly that the amplitude modulated wave has a carrier. You know that this is a carrier signal, as we expressed before. This is a carrier wave, not true? EC sine 2 pi fc. That's the carrier, right? So the amplitude modulated wave that after I mix it, it has the carrier, yeah, and so it has the unmodulated carrier plus it has a constant plus the modulating signal. Where's the modulating signal? The modulating signal, see, right here. But what's in front of it is a constant, right? Now that we have the expression like this, we also should notice something else. What we should notice is that the same AM wave that we have right here, if we do the maths, it means that this times this would give you this. Agree?
Yes, sir.
Okay, so this, we're expanding now. This times this, giving you this. Everybody see that? Plus, this times this is going to give you M EC, which is right here. So M EC, and then we're going to have an angular expression, sine omega, or sine 2 pi MT times sine 2 pi FCT. That's what we have left here. Now, ladies and gentlemen, this here is an expression that we can use double angle and apply.
Oh, yeah.
Sine of A, sine A, sine B. What is sine A, sine B? I'm gonna leave it there for tonight. You're gonna go back to your math and you're gonna try and remember or come up with what it is. It's actually right here. We try and go
I was
back.
about to say so because I remember that sine A, sine B would be a half cos A plus B plus a half cos A minus B.
Absolutely. And that's exactly what happens here. That's exactly, so if you notice, this part is still here. And then by using the double angle formula, sine A, sine B, we would get minus a half, because remember now this is a half, right? This is in front of it, so that becomes MEC over 2, so that's where the half come in, right? Cos 2 pi angle A plus angle B plus a half cos angle A minus angle B. That's what this part sine A sine B is. So for those who need to go and get a refresher, that's what it actually equals to. Okay? Equals to a half cos A minus cos B minus a half cos A plus a minus a half cos A plus B. So that's what sine A sine B equals. So that's why we're able to expand here into double angle format and get all of this, including the minus sign. All of this. Okay? And from here, you can see a couple of things. You can see that the amplitude modulated wave incorporates the original carrier signal, plus, 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 these two, which is called here, is because the frequency are added, FC plus FM is called the upper sideband, and where the frequency are being subtracted, it's called a lower sideband. So an amplitude modulated wave has both a lower and an upper sideband plus the original carrier. Now, where is the information from here, ladies and gentlemen? Because this is now the modulated wave now. And this modulated wave is now being sent over the transmission medium, nicely protected towards the receiver. When the parents reach to the school with a child, the parents need to go home. They have done their job. So you don't need, so really and truly in an amplitude modulated wave, you don't need the parents anymore, which is a carrier. What you really need is what? The information, agree?
Yeah.
Okay. And information is here in the form of FM, but it's on two sideband, here and here. This is the upper sideband because it has a plus, and this is the lower sideband of frequency. So you don't need a carrier anymore. But what you'll find happening, ladies and gentlemen, is that these two are identical. They have the same amount of information. It's just that this is on one end of the frequency spectrum and this is on the other end of the frequency spectrum, which doesn't really matter because the information is inside it. So here we have FM, so information is always inside of these two. So the truth be told is that an amplitude modulated wave is going to have the carrier frequency, which is there, plus upper sideband, and which is here, all of this actually, and a lower sideband, LSB. So that's how the amplitude modulated wave is. However, ladies and gentlemen, you need to understand that after the modulation process and the transmission of the wave, and sometimes even before the transmission of the wave, you don't even, because even at the transmitter, you can now remove the carrier because of the fact that we know how the wave is going to be, the AM wave. We can remove the carrier. Now that's when you remove the carrier here, you are diminishing the wave. It is already protected. It's protected in the sidebands. But you can remove the carriers, and you can also remove what? One of the sidebands, because the same information is in this sideband, the same information is in this sideband. So that's why Ms. Watson was talking about, you have what is called, in AM wave, you have what is called the double sideband full carrier, which is all of this, what is here, or you have the double sideband suppress carrier, which is eliminating the carrier here, so you only have the two sidebands. Or you have single sideband, as I mentioned to you before, because the information in the upper sideband and the lower sideband are identical. What it means is that you don't need both sidebands. So you can actually get rid of one of the sideband. So that's why the amplitude modulated wave can now be transmitted as a single sideband.
Sir, excuse me, sir. So that means if some of the information is corrupt, you still probably can get from one side.
Yeah, well,
both of them.
The information won't be corrupt, because if it's corrupt, it's going to be corrupt in both. Because these are identical. What happens is just only the band of frequency changes. And we're going to look at that next week. But the information is identical.
Protected.
I'm sorry?
If it was protected, it was protected. So
Exactly.
I mean,
Exactly.
you can't have it being corrupted at the same time while it is being protected.
Well, it can, and that's that's for the upper level of communication theory. You're gonna be looking at noise is something you can never get away with. So noise, we have to find ways and means to get around it. But for now, learning it is, you don't have to worry too much about it at this stage. So what we're doing, as I say, we can have either the complete transmission of this or remove the carrier and transmit only sideband. What that one is called again, Miss Watson? Are you still here with us?
I am here, sir.
You remember when we remove the carrier from it, what it's called? The AM transmission? It's double sideband suppressed carrier. Or there's another fancy name. It soon come back to you, the one you couldn't call before. So in other words, what I'm saying is that this is what comes out of the amplitude modulated wave. But lots of times it saves you a lot of other resources than to transmit all of this. Once you have the wave modulated, we could simply use a filter to remove the carrier. We could also use a filter to remove the carrier and one of the sidebands, because we know the frequency, right? So remember, filters act based on frequencies, right? So we know the frequency of the carrier, we know the frequency of the sideband, whether up or lower. So we could just basically remove these two from further transmission, still having the signal in one of the sideband and transmit the sideband. It then makes it more productive in doing it that way, because you'll be using less power to transmit the AM wave. And power is important, because instead of building a big tower with a lot of power requirement, you can actually build a big tower with more directional gain transmission and using less power. If we get rid of the carrier and one of the sideband after the AM wave has been mixed, so you'd be using a quarter of the transmitted power in transmitting one sideband as compared to transmitting entire AM wave as is.
Sir.
We're gonna leave it there.
Sir.
I tell a question, but we're gonna leave it there just to make sure remember where we left off. And we'll talk about power next week. We're gonna show you how it is that power affects amplitude modulated wave right here. Again, this is also placed in the Google Classroom. You can get access to this information. Go ahead, Mr.
Go back to you. Yeah. In terms of one of the sidebands, you're saying that one of the sideband, for example, it would be minus MEC over 2 cos, and whatever is in the bucket. That would be one of the band, right, sir?
All right, let me do it this way. Let me do it this way. So the amplitude, remember now, this is after modulation. Remember I showed you in the transmitter how you mix it to two signals, right?
Yeah.
Right. So this is after they have been mixed now using amplitude modulated wave. Mathematically, we realize that the expression for the composite expression, the expression for the composite amplitude modulated wave is going to be this expression. That expression shows us that clearly we have the original unmodulated wave. We also have two sidebands to include the upper sideband right here. And don't watch the minus sign. Why it's called, this minus is right here, and don't ever forget it. Very important. So I'm going to erase that. So that's the carrier. This is the upper sideband because here you're adding a frequency. So that frequency is going to be higher than the original carrier frequency. That's why it's called upper. Whilst all of this is going to be your lower sideband. It's called lower sideband only because of the fact that that frequency is going to be lower than the carrier frequency. Hence we call it the lower sideband. That's the question you're asking?
Yeah, man. No, I understand it. Yeah.
Okay. And again, I said to you, now that we've seen it this way, we can transmit the whole of this from transmitter to receiver. Or we can choose to transmit the sidebands only. Because you realize that if you look, this is half of the voltage that is here, right? So half and half. So this is, we add up all it, and we're going to show it later in the power. You're going to see that you're only going to need one sideband, truth be told, because the same information that is here is the same information here. So you don't need to have the carrier anymore. You don't need to have one of the sideband, anyone. You're going to need one sideband to really transmit the needed message. And that is why I say that once you fix the thing, so this is now realizing that you needed the intervention of the parent, right? But the parent could actually intervene in carrying the child, going on the bus, which is what we have right now, and up and down with all of this problem. Or the parent could try to make it easier for him or herself by saying, okay, I've intervened. What I've done now is place. I remember you guys gave me a lot of these options when we were talking in either last week or the week before.
Yes,
where it was, okay, we're gonna put a child on a cab. So you don't need to, parents don't need to go anymore because you have the intervention. The whole idea is the child reaching school. So this is one option where you're moving the parent, but the parents had intervened because without the parent, that arrangement to have the cab would not be there, But the parent does not necessarily have to go with the cab or the bus or the bicycle as somebody had mentioned before. Or the bike taxi that somebody had mentioned before. The arrangement is in place. So you don't need to carry the parent or the other sibling, but you just need to carry one of the sideband, which is the taxi taking the child to school for the child to reach. It becomes cheaper eventually, and less human resources being expended. Cheaper from the perspective that if the parent took the bus, they would have to pay fear as well as fear for the child. Plus, it might inconvenience the parent in terms of taking him or her from something that needed the attention, probably to make money anyway, like to go to work. So that's why that intervention, in this case, means that you could have options. And the options has, options, they do have repercussions or implications. So as I said before, one of the things that one of the things it could do is to remove this excess power, excess carrier and sideband in trade-off for power. So you don't need so much power, or you don't, and in this case for the parent, you don't need to spend so much money or spend so much time away from work to carry the child up and down to school, but put something in place and the child will still be transported effectively and efficiently. So that's like you saying, okay, we're just going to send one sideband instead of transmitting two sidebands plus the carrier.
So all of this is important when designing a circuit to ensure that it is cost effective then.
Absolutely. Absolutely. You're going to find a little bit later on that the choice of using whichever method you select saves you like 75% on the power usage, the amount of power you can use. Now, there are two things that are important in telecommunication: power and frequency. You do not have frequency lying around that you can use arbitrarily. The frequency band is fixed, and there are a lot of users out there that are using frequencies across the frequency band already. So it means that if you're going to be using a frequency, you have to make sure you use a frequency as efficiently as possible, as effective as possible. Now, comes with frequency is the power. How much power you apply to transmit this frequency from point A to point B. So, and I'm just using it arbitrarily. So, RFM needs to transmit. So its transmitter is somewhere in the hills of St. Anne. So it has a frequency already. But when you're in Montego Bay or Westmoreland, you're not picking up RFM properly. So it means that they need to boot the power of the transmitter. Boosting the power of the transmitter is not something that it's not a linear relationship between boosting the power of the transmitter and the cost. It takes a lot of money to be able to develop transmitters that are as powerful or more powerful in terms of transmitting power at the same frequency and also adhering to the regulator's terms and conditions. So you're going to have to get a transmitter that's going to transmit at a higher power and transmit that you don't interfere with your other frequency-related operations. So other radio station, police transmission, etc., etc. So you have to buy now a more expensive and a more sensitive transmitter. That's what we're talking about in terms of trade-off with frequency and with power. So if you're choosing to transmit the full double sideband full carrier as compared to single sideband suppressed carriers, you're going to have a trade-off in power, and you're still not losing the information that you're trying to transmit. So that's where I want you guys' mind to be, because this is important. This is not just about doing something, and I know that you guys are taking the course, but this is not just something about that. This is what we're talking about now when you get into an industry or when you start to think as an engineer. What are the things you need to think about? So, like somebody loosely said before about 5G, you start to get the kind of concept we're talking about now. That whilst 5G has a technology with the frequency within a certain band, if we do not transmit 5G at a certain power level, it has limited reach and by extension, limited effect on people. Think about somebody. I don't know if you guys ever look at a cartoon and they say the people are zapping people or zapping things in a cartoon.
Yeah, man.
That's what happens when you turn the power up at a certain high frequency. It starts to now penetrate things more with more power, and it becomes dangerous. And that's why
Cancerous.
and that's why microwave, and not microwave as in microwave oven, but microwave frequency band, it is important to adhere to power regulation because it means, not because it means that you can transmit your thing further with wider coverage. You have to think also about the power as it relates to having side effects or affecting things, people, and places. So that's kind of the reason I wanted to understand. I'm going to leave it there for tonight, ladies and gentlemen. Are there any questions based on what we covered so far that you have?
Sir, we have this. When we have this.
When you have a test?
No, we're just getting on the course.
That's nice. All right, so we'll finish AM, we're going to give you a test. See if you really understand AM.
No.
So we'll get a test every other week.
Is there any course outline?
Course outline, I didn't send it?
I see a textbook.
I said, right. Well, you see, all that I'm explaining here, it's all in the textbook as well. This is specific to AM. It's all here. So I didn't put up a course outline. Devices to put a course outline. All right, so I'm gonna send you a course. I'm gonna post a course outline on in the Google Classroom. All right.
All right.
Yes, sir. One more question. We have lab tomorrow, sir.
Okay, lab. No lab. We just start this thing, so we have no lab.
All right, boss.
Next question.
I'm sorry. Yes, sir. What I really want, I want to gain the engineering knowledge and understanding regarding this course to understand more about these cell towers that are being put up by the communication service provider at close proximity to homes and within communities to understand whether if there's any negative implication as a result of having these cell towers. So that I don't really understand things from a layman's standpoint, but able to bring some rationality in reasoning and explanation to the layman.
Okay. All right. Well, I will continue to emphasize what is important without losing track of what we need to do to cover full coverage of the course. All right. There are higher level courses. I think there are some electives in the communication area that will cover all of those. But I still can, for all my years of understanding experience, what I would normally have done, this is what your group would have encountered. If things were normal, you guys would be going. So for all the guys, the groups before you, that have done communication, what I did was to take them field trip. So they have gone to Nationwide, CVM, Digicel, eras that cover all the eras. I think Aerotel as well. That cover the eras that you'd have gone and see not only what we were talking about in theory, but you'd have gone to the class, to the locations, and their engineers would have gone through and explain inside studio, outside studio, inside a plant, outside of the plant in terms of like a Digicel and Aerotel. So you'd have gotten all of that, but we can't impose ourselves on people anymore due to the pandemic. But we do as much as we can to help you to do that understanding. So that's where you'd have gotten that knowledge, Mr. Delroy. That's where we'd have gotten that extra hands-on knowledge, okay?
Okay, sir.
All right. Guys, go to your bed. Enjoy your night. Tomorrow, you do not have lab sessions. So utilize that time frame, please, to get more insightful information on information that has been posted, all right?
Sir, everybody I go sleep, sir. I tell you. I know, everybody I go sleep.
Well, everything has a price.
A joke, sir. All right, sir. We see you next week.
All right. Have a good night. See you next week.
All right.
All right, then. Bless up yourself, sir.
Yeah, man. Take care.